Pick up with chapter 11, and today we're looking a little bit at stoichiometry. Now, stoichiometry is that big word. We've talked a little bit about it in the past, but we kind of get scared about that word because of some of the things that we see that it might entail. We look at the infographic here in the bottom of the page. You see things like mass and reactions and gas quantities and laws and hydrogen and products reactants. Stoichiometry describes all kinds of words that come up when you talk about stoichiometry. But really, what is stoichiometry? Okay. And as we take a look at stoichiometry, the first thing that we're going to find out is that the way I define stoichiometry is chemical math. It's how we can use math and chemistry to make certain predictions about reactants and products. In reality, the word comes from the Greek meaning elements for stoicheion and metri for measurements. So we have element measurements is what we're talking about when we're looking at stoichiometry. And so what we really are dealing with is we're dealing with balanced chemical equations. We've looked at moles and stuff like that in our last chapter, but just dealing with a certain element or a certain compound, now we're actually be taking a whole chemical equation and finding out how many reactants and how much products there are if we know something. If we know one thing in the reaction, we can find out how much of any other reactant we're going to need or how much product can be produced. Or vice versa. If we know how much product we want to make, we can figure out how much reactants that we're going to need to make that.
I go up to the bar and write down the simple passes. P, H, and AT. We use that method all day.
You can check that video out on your own. Watch through this because we're going to teach you how to stoich in this chapter. Stoich as in kind of get the idea already from that little bit of the video you saw. So that's for you to watch here, or you can also see it on the website. And we'll probably take a look at it in class. But just kind of goes through again, stoichiometry. Or maybe we can say in this chapter too that we're going to see that we have all the elements that we need to have something exciting happen. You're just dying at my jokes today, aren't you? Okay, so basically as we get back to it again, stoichiometry is one of those very important tools that chemists use. We use again to be able, as I said, to predict how much product we're going to form from a given amount of reactants or how much reactants we need to get a certain amount of product. So it's really going to be an important tool because it lets us be able to do so many things. It really makes chemistry be powerful. Instead of just knowing, hey, this is the type of reaction, it lets us actually say this is how much we have, this is how much we're going to get. And so, as you see, they said these guys are still very important in this chapter. They're extremely important. That's why we talked about them a lot in the last chapter. And we're not necessarily talking about the star-nosed guys, but we're talking about moles in general, right? And just like that's such an ugly picture that it's cute, right? So basically, a chemical equation is very similar to a chemical formula. It gives us two pieces of information, and the exact same piece of information that the chemical formula gave to us. Number one, it tells us how many particles there are in each substance, how many atoms of each element are in one molecule or formula unit of that substance. And again, atoms stand for elements, molecules for covalent compounds, formula units for ionic compounds. But even more so, it tells us the number of moles we have of each substance in a mole of compound, or how many moles of each substance we have in the reaction reacting with each other. And which one is more important for us, do you think, right now? I give you a hint. Think about bigger letters. I think you got it. That's going to be our whole basis for what we're really doing in stoichiometry, the number of moles of each substances and how they're reacting. So what we take a look at is the important key here, the really big key to doing anything in stoichiometry is realizing that there's this thing that we call the mole ratio. And the mole ratio is our gateway from getting from how much we have of one substance to an amount of another substance in our reaction. And it's just the ratio of moles, and by moles in this case we're talking about the coefficients in front of your substances in your balanced equation. It's a ratio, so a fraction, where you take one substance over the other substance. The substance we're looking for over the substance that we have been given or that we know what it is. And that's our mole ratio. It's telling us how many of each one it takes to react together. So we can always write that very simply, a mole ratio like this. A mole ratio is always going to be the coefficient moles of the stuff that we want or that we're trying to find divided by the coefficient moles of the material or reactants or products that we are given. That's your mole ratio. With that value, you can change from one substance to another substance very easily. So basically, you can kind of think about a chemical reaction like being a recipe, where you have this base recipe. Let's say it takes 2 eggs and 1 cup of flour to make 3 pancakes. What if I doubled my number of eggs? What if I had 4 eggs? How many pancakes could I make? I could make 6 pancakes right now, assuming I have enough flour. By changing my number of things that I have, I change how much I can produce. That's what a chemical equation really is doing. It's telling us what the simplest whole number ratio is, but if I know how much of any one substance I have, I can use that ratio in order to find out how much of the new product I'm going to have. If I double something of one substance, then I'm probably going to get some ratio of another substance that's going to be bigger than what it was. So all we're going to do is we're going to take, once we get or we have the number of moles of a given substance, we're going to multiply it by a mole ratio, and that will give us the moles of the substance that we're looking for, which may be our answer, or we may be looking for another quantity, grams or milliliters of a substance or liters of a substance, which we then can very easily change into. The grams part you already know how to do. The volume part we'll get to. So again, we can get from any quantity of a given substance to any other given quantity of a substance that we want to get by using our mole ratio. We change to moles, we multiply by the mole ratio, gives us moles of our new substance, and then we can change that into whatever quantity that we need to have at the end. So here are different types of problems that we can do, and they're all really closely related to each other. Mole-mole, mole-mass, mass-mole, that's really the same thing. A mole-mass and a mass-mole problem, just that the first term is usually what we start with. We're going to be given a number of moles, and we're going to try and find a number of moles. Or we're given a number of moles, we're trying to find the mass of a substance. We're given a mass, we're trying to find the moles. Mass, volume, so on and so forth. But they all have the exact same thing in common. They all are taking your given quantity, getting to moles of the stuff you want, and then changing that back into the quantity that you want to get. So they're all 3-step problems. So here is a basic flow chart that's really showing us what we're going to be doing here. Depending on where we're starting at, we start with whatever we're given. If we're given a mass or a volume of a substance in the equation, we start at this blank, and then we switch to the moles of that given substance. Okay? Moles is grams divided by molar mass if we're given a mass. If we're given a volume, and we'll talk about this later on, we would do this conversion. We would take our volume divided by 22.4, and we'll talk about what that means a little bit later on, where those numbers come from. But basically, we're going to be starting mostly with mass or moles. If I'm given the number of moles of a substance, then I'm just going to be already starting right here. But that's what we're trying to get to. We're trying to get to moles here because, again, the chemical reaction tells us moles of our substances. And if we have moles, then we can multiply by the mole ratio, the coefficient moles we want over the coefficient moles given, and that gives us the moles of our wanted substance, the stuff that we don't know that we're trying to find. And if we want moles, that's our answer. If not, how do we get to our wanted quantity, whether it's mass or volume? Grams is moles times molar mass, or volume is moles times 22.4 liters per mole. Okay? Very simple. It goes pretty quickly. But the whole key, again, is in realizing what's happening in this section right there. We're talking about we have to know how many moles we have, because then we can use our balance equation to find out how much substance we have of our unknown substance, stuff that we're trying to find. So that we're trying to get to moles, we switch to moles again, then we can switch back to any given quantity by those couple of equations. So here's an equation, here's a problem. In the balanced chemical equation, C3H8 plus 5O2, which is propane plus oxygen, propane burns in the presence of oxygen to form carbon dioxide and water. How many grams of water would be produced from the combustion of 100 grams of propane? So if I burned 100 grams of propane, how much water could we form? So what I did is I rewrote the chemical equation just like they gave it to me. Sometimes it'll be balanced, sometimes it won't be balanced. If it's not balanced, you'll have to balance it. And then I put in right underneath my equation my known substances and my unknown substances. So notice in this case I put 100.0 grams right underneath the propane, and I put the question mark grams under the water. That's telling me what I have, I'm given grams, and it's telling me what I'm looking for, how many grams. Excuse me. Someday we'll get that taken care of. So again, the 100.0 grams is what I'm given, and I'm looking for how many grams of water. Now we can't compare grams, okay? Because when I look at my balanced chemical equation, those numbers in there, those subscripts are telling me how many atoms or molecules we have or how many moles. But if I have grams, if I have grams of propane, I can find out how many moles I have. Moles is grams divided by molar mass. So that would be 100 grams divided by the molar mass of propane, which we find by taking your element carbon, 12 times 3 is 36, so H is 1 times 8 is 8, and add them together get 44. Okay, so 100 divided by 44 is 2.27 moles of propane. That's how many moles of propane. Now, I could say, okay, if I have 1 mole of propane, I'm going to get 4 moles of water. If I have 2 moles of propane, I'm going to get, that's right, 8 moles of water. If I had 10 moles of propane, 40 moles of water. If I have 2.27, okay, notice what I'm doing there is I'm taking whatever this number is and I'm multiplying by the ratio of 4 to 1. That's what the mole ratio is doing. That's a pretty easy one to pick up in your head, but we want to be able to write that down for when the ratios aren't quite so easy to calculate. Okay, so there's my balanced equation again. Now I have 2.27 moles. Your mole ratio, to find the moles of your wanted substance, I want water, that's going to be the coefficient moles of wanted over the coefficient of moles of given. What do I want? I want the question mark. Water. What's in front of water? 4. Coefficient moles of given, that's what I started with, that's what I knew. What did I know? I know the propane. What's in front of it? 1. So my mole ratio is 2.27 moles of propane times 4 moles of water per 1 mole of propane. Okay, that's where the 4 and the 1 come into play. They are coming from our balanced equation. The 4, change colors here. I want the 4 because that's where my question mark is. That is my coefficient moles of what I want. And my given substance is what I started with. That's a 1. That's where that number comes from. So that gives me 9.08 moles of water that are going to be formed. Okay, that's my conversion. But I'm not done yet because they actually asked me for how many grams of water I had. So I need to change moles of water into grams of water. And grams is moles times molar mass from our flow chart. In fact, from the flow chart for this chapter too. And that's going to be our moles times the molar mass of that compound. Here's a very common mistake. We'll say, okay, I found 44 back here for propane, so I'm going to put 9.08 times 44. It's the molar mass of your given substance or your wanted substance. It's the moles of water times the molar mass of water. These two quantities should be for the exact same substance, so keep that in mind. And so that gives us 163.4 grams of water. Okay, pretty straightforward. And that's what we call a mass-mass problem. I was given a mass, and I was looking for a mass. And that's really, until we get to a little bit later in the chapter when we talk about limiting reactants, is really our toughest type of problem. Mole, mole volume, we're all pretty simple. It's just when you do mole mass, you have more steps to do. But it's pretty straightforward. Find the moles, multiply by the mole ratio, change back to the quantity that you want. And now just a little bit of humor for you again to finish up today's lecture. Just you might get a small kick out of a couple of these, and guys, you can maybe try that middle one there as a pickup line. Probably won't work, but you could try. But the other two, the one on the right and the one on the bottom, are ones I know you probably will get frustrated at times with some of this stuff, but keep in mind it's doable. You can all handle this, and it's a very important skill that chemists have. Okay, we will see you on Monday.